Hey guys, we're going to start reviewing for the Unit 3 exam. Take notes on this as you go, and it'll help you prepare for the Unit 3 exam. So a car with mass m possesses momentum of magnitude p. Which expression correctly represents the kinetic energy of the car in terms of m and p? So P equals mv, which in its transformed form would say that V equals P over m. This is useful because I'll be able to substitute a P over m every time I see a V. For instance, as I encounter the kinetic energy equation Ke equals 1/2 mv squared, I know I need to replace the V with a combination of P over m. So I'm going to do that now. I need to write P over m squared because the V was squared, and with simplification I get Ke equals 1/2 mp squared over m squared. So this m is going to cancel with the square of the m, and that's going to leave us with 1/2 p squared over m. So I believe choice 4 is our correct answer. So moving on to number 2. The table below lists the mass and speed of each of 4 objects, and which 2 objects have the same kinetic energy. So I put in my base equation, and then I substituted in for the values from the table. And I was able to find by following through with my solutions that these two actually result in the same value, so the 2 objects that would have the same kinetic energy would be objects B and C, or choice 4. Number 3, during an emergency stop, we have a 1,500 kilogram car losing a total of, 300,000 joules of kinetic energy. And what was the speed of the car at the moment the brakes were applied? So we'll start with the equation Ke equals 1/2 mv squared, but we'll rearrange for V. So initially I see that V squared is Ke over 1/2 m, and we can take the square root of both sides to find that V equals the square root of Ke over 1/2 m. So we'll substitute now. So without taking the square root, I'm getting 4.0 times 10 to the 2. I was able to do that in my head by just doing 10 to the 5 minus 10 to the 3 and getting 10 to the 2. And then the 3 over 1.5 is 2, but then divided it by half is the same as multiplying it by 2, so I got 4. And after you take the square root of that number, which is really 400, so the square root of 400, you get your final answer as 20 meters per second. Next one. If the direction of a moving car changes and its speed remains constant, which quantity must remain the same? I'm going to go with kinetic energy on this one. Because kinetic energy is it's energy, and energy is not vector, so the direction doesn't really matter. But the speed does matter, so if the speed changes, or it would be a different kinetic energy, and if the speed stays the same, it would be the same kinetic energy. Number 5. The diagram below represents block A having mass 2m and speed v, and block B has mass m and speed 2v. Compared to the kinetic energy of block A, the kinetic energy of block B is. So these are my sort of base setups. I'm basing them on Ke equals 1/2 mv squared, but I am putting in the appropriate differences, whereas block A has 2m and block B has 2v. I would like to make a note that the kinetic energy for block A is going to be a simple doubling because of the doubling of the mass and the direct relationship between mass and kinetic energy. But the kinetic energy of B is going to be a quadrupling because of the doubling of speed and the square of that double. So double squared is going to give you 4, and that's why we're going to have 4 times as much energy in B as compared to normal. But compared to the energy of A, the energy of B is just twice as great because 4 is twice as large as 2. So in number 6, we have a car that's traveling at constant speed up a hill. And as it goes up the hill, you are gaining height, which means that you have a change in potential energy, which is increasing. So you're getting more potential energy. But it's also moving at constant speed, which means that your kinetic energy is constant. So in that case, our answer choice would be that gravitational potential energy increases and kinetic energy remains the same. In number 7, we have while riding a chairlift, we have a 55 kilogram skier, which is raised a vertical distance of 370 meters, and we want to know the change in potential energy. Well, this one's pretty straightforward because potential energy is mgh, and we know the mass is 55. We know that gravity is 9.81, and we know that the change in height was 370 meters. So I got a really large number of joules and I went ahead and converted it into scientific notation, and I'm able to match that up with choice 4. So in number 8, they're asking for the work done on a slingshot, and we see that the work done on the slingshot is 40 joules to pull this stone, this 0.10 kilogram stone backwards, and the slingshot will project the stone straight up in the air. They want to know the maximum height to which the stone will rise. So we know that if 40 joules of work is done to load the stone, then we know that it's going to give the stone 40 joules of kinetic energy when it begins to fly. So we also know that if it has 40 joules of kinetic energy when it begins to fly, it will rise to a height that has 40 joules of potential energy above the ground. With that said, we know that the potential energy will be 40. We also know the mass of the stone and we know gravity, so we can really easily determine height. So after rearranging and plugging in, I got 41 meters as the height to which the stone would rise. Next up, we have a 60 kilogram student climbing a ladder a vertical distance of 4 meters in 8 seconds. And we want to know how much work is done against gravity by the student during the climb. So the work done against gravity could be described as the change in potential energy here. And potential energy is simply mg change in height. So from there, I know that the student's mass is 60. I know that gravity is 9.81. And their change in height is 4 meters. So I'll use those things to calculate the answer. And I'm getting 2354.4, which would round to 2.4 times 10 to the third, and that would be choice 1. So for the next one, number 10, we have a child pulling a sled at an angle, right here, 25 degrees. They want to know how much work does the child do in moving the wagon a horizontal distance of 4 meters. So the horizontal work is going to be just the horizontal part of this force. So the force that we'll use is not just 20. But the equation that we'll use is essentially work is force times distance. But the force, we'll need to do a calculation first. And after putting in the equation ax equals a cosine theta to find the horizontal part of the force, I'm able to see that the horizontal part of the force would be just about 18 newtons. I'm going to write down 18.1 newtons just for fun. And I'll use that to plug into my equation W equals Fd. So that means that W is going to be 18.1 times the distance of 4 meters. And I'm getting 72.5 as my answer. So 72.5 joules, since this is work. So 73 is my closest response.
So when we're thinking about the relationship that exists between the elastic potential energy stored in a spring and its elongation from equilibrium, I recommend using the following equation. So the elastic potential energy would be symbolized here, and the elongation from equilibrium is this guy. So this relationship is a direct squared relationship, meaning if I increase x, PE will increase by its square. So the only diagram which properly displays a direct squared relationship is going to be choice 2. All right, so number 12. A 2 kilogram block sliding down a ramp from a height of 3 meters above the ground reaches the ground with a kinetic energy of 50. And they want to know the total work done by friction on the block as it slides down the ramp. So we have our block here, it slides down the ramp. When it gets to the bottom, it has 50 joules of kinetic energy. And they want to know how much work has been done by friction. So the best way to think about that is to think about how much energy should it have had when it got here had there been no friction. And then we'll look at the difference between that value, and that'll give us the work that was done by friction. So I recommend actually solving for the potential energy of the block at its 3-meter height up here. And that is going to be equivalent to the amount of kinetic energy it would have in an ideal mechanical system as it reached the bottom of the ramp. So if the block had 58.86 joules of energy stored as potential at the top of its ramp, it would slide down an ideal ramp and reach the bottom with a kinetic energy of 58.86 joules, but it only has 50 joules of kinetic energy, which means that the work done by friction, which is the work that opposes the motion of the block, must be 8.86 joules, or about 9 joules. So I'm going to go with 9 joules right here. All right, so which quantity is a measure of the rate at which work is done? This is a very decent definition for power. All right, so let's do this one. So we have a person who is exerting a 600 Newton force this way along a rope. So according to the crate, it's going to be going sort of like that. And the crate, it has a mass of 50 and it's being raised 3 meters in the air. So we can do an analysis, which is like a potential energy analysis. We can see how much potential energy it gains as it goes that way. But additionally, they want us to compare the work that's done by the student. So ostensibly, they're asking us to use an equation, work is force times distance, because they give us the force that the person's exerting, and we know that the distance is going to be 3, or the number of meters that the crate's being raised in the air. And they want us to compare those two to see if they are the same. Now, in an ideal mechanical system, they would be, but they never say this is ideal, and they never say it's friction-free, so it leaves it open to the possibility that they might be different. So let's do 2 analyses, a potential energy, and also one for work, and we'll see what happens. So in the potential energy analysis, we know that the mass of the crate is 50. Obviously, we know that the acceleration due to gravity is 9.81, and the height gained by the crate is going to be 3, meaning that the amount of potential energy gained by the crate is 1471.5 joules. We're paying no attention to significant figures. And when we do the same thing for work, we just need to use the amount of force which was put on the crate, and that's 600 newtons. And the distance it's being raised is 3. So that means that the amount of work done against gravity is 1800 joules. So I can see now that there is a difference between the two. And when I come back to the text of the question, it says, compared to the work done by the student, the GPE gained by the crate. The GPE is less than the amount of work done by, let's see how much. I'm seeing that there's a difference of about 328.5 joules. So the GPE gained by the crate is 30 joules less than the amount of work done. Okay, next up, what's the maximum amount of work that a 6,000 watt motor can do in 10 seconds? So starting from the equation P is W over T, I know that I can solve for work by doing this. Work is P over T. So we can plug in from here. The amount of power is 6,000 watts, and the amount of time there is 10 seconds. So that means that the amount of work done is 600 joules in 10 seconds. The best answer choice is 2. Student A lifts a 50 Newton box from the floor to a height of 0.40 meter in 2 seconds, whereas student B lifts a 40 Newton box from the floor to a height of 0.50 meters in 1 second. They could ask us about work or power here. Let's keep reading to see what. So compared to student A, student B, Okay, they're asking us about work and power, so let's solve for both. So I set up a little table. We have force times distance for work. We have work over time for power. And I'm going to go ahead and do the work equation for A and for B. So for A, we have a 50 Newton box in 0.4 meters, and for B, we have a 40 Newton box and 0.5 meters. I've discovered that both answer choices are 20 joules. So I know that it could not be choice 3 and it could not be choice 4. Now for the power calculations, we'll just need to take our answers for work and divide them by time, and I'll do that now. So you can see that student B is has dissipating more power. So let's see. Compared to student A, student B does the same work but develops more power. That's going to be choice 1, best answer. Okay, so for 17, we have a boat whose weight is 900 newtons, but it requires a 600 Newton force to move it forward at a speed of 1.5 meters per second. I guess that would be 15 meters per second. So the boat's engine must provide energy at the rate of. So if they're asking me about providing energy at the rate of, they're really asking me about power. So I know that the answer has to be in watts, and I just noticed that choice 1 and choice 3 can't be the answer because they're in joules. So we'll come back to that in a minute. But which of these forces is the best one is a good question. But the 900 Newton weight is not going to be the force that you need. We're going to need this horizontal force matched up with its horizontal speed. And that's how we'll know that those two go together. So let's do a power equation. Let's use P equals F by change in V, or excuse me, average V. So the force pushing it forward is 600 newtons, and the average speed there is 15. And when you multiply those two together, I believe you get 9,000 watts. So that'll be this one. Nice. Okay, great. So on to the next one. A 110 kilogram bodybuilder and his 55 kilogram friend run up identical flights of stairs. But the bodybuilder reaches the top in 4 seconds and his friend takes only 2. Compared to the power developed by the bodybuilder while running up the stairs, the power developed by his friend is. So power is work over time, but work is force times distance. So that means that power is also force times distance over time. So for these two bodybuilders, their distances are going to be the same because they're running up equal flights of stairs. But for the heavier bodybuilder, you're going to be having twice the force. And for the lighter bodybuilder, you're going to have half the amount of force. But there's a difference in time as well. For the heavier bodybuilder, he is reaching the top in 4 seconds, while the lighter bodybuilder is reaching the top in only half that amount of time. So I'm going to compare these two with a really basic analysis. So if we say that the bodybuilder has twice as much weight, but it also takes him twice as much time, then you can see that in terms of power, those two sort of factors of 2 cancel out, and you end up getting just a really normal F times D over T. And then you're comparing that to the friend who had a normal weight and normal time, so I didn't multiply either of those by anything, just FD over T. So these two are coming out to be equal. And I would just point out that that means that they would be developing the same power. So a horizontal force of 5 newtons acts on a 3 kilogram mass over a distance of 6 meters along a horizontal frictionless surface. What is the change in kinetic energy of the mass during its movement over the 6 meter distance? So we all know that work has the ability to change an object's energy, and that could be kinetic energy or potential energy depending on the direction of the object's motion and depending on the direction of the force. In this case, the object is moving horizontally and the force is also horizontal. So I'm going to use a really classical equation, work is force times distance. And the amount of work that I solve for, the horizontal work, is going to be the amount of work that has been done on kinetic energy. So while it won't tell me the actual kinetic energy of the block, it will tell me how much the block's kinetic energy has increased. So 30 joules, and that means my answer is 3. All right. In this graph question, we are ultimately being asked for the amount of work done in moving the box 6 meters, and work is force times distance. And on this graph, we have on the axes force and distance, which is amazing because all we need to do is multiply the y-axis by the x-axis to get the work. However, when we multiply the y-axis by the x-axis, we are really doing an area under the curve analysis of the graph. So this area under the curve is going to be a rectangle combined with a triangle. So we'll need to use two different equations. We'll need to use the basic area equals BH, but we'll also need the slightly less basic area equals 1/2 BH, and then we'll combine those for our answer. So I got 18 for the rectangle and 9 for the triangle, and when you combine those two, you will get 27. So 27 joules is the amount of work that was done in moving this particular box a distance of 6 meters. And the next question, they want to know the work done in accelerating an object along a frictionless horizontal surface. That would be equal to the change in the object's kinetic energy, just as we have discussed. So if we have a 1/2 kilogram ball and we throw it up in the air with an initial kinetic energy of 25 joules, it's possible to figure out how high the ball will rise if we understand that the 25 joules of kinetic energy that it begins its flight with, that will be converted to potential energy. And then working backwards from there, we can figure out the height that the ball is at. So, if the 25 joules is going to become potential energy, and potential energy is really just mg change in h, then we can pretty easily figure out that the height the ball reaches is really just going to be its potential energy over its mass and its acceleration due to gravity. And I got 5.09 meters as the height that the ball would reach. The best answer here is 5.1. Alright, so in 23 we have a moving 5 kilogram cart at the foot of a hill, and the hill is 10 meters high. For the cart to reach the top of the hill, it doesn't have to keep going, it just needs to reach there. What is the minimum kinetic energy that the cart would need? Alright, so understanding that the potential energy that the cart has at the top of this hill would have to be at least equal to the kinetic energy it has right here as it's about to go up the hill, then we can just solve for the potential energy and then call it the kinetic energy. So the potential energy is mg change in h, and the mass of this cart is 5 kilograms. The gravitational acceleration is 9.81, and the height that it must reach is, of course, 10 meters. So that means that the potential energy that it would have at the top of that hill is 490.5 joules. So if that's the amount of potential energy it has to have at the top of the hill, that's also the amount of kinetic energy that it must have down here at the bottom of the hill. Therefore, the best answer is 491 joules. Okay, so in 24 we have a 3 kilogram mass, which is attached to a spring with the spring constant of 30 newtons per meter. So this is our mass, spring constant K. The mass is being pulled by 0.2 meters, so this is going to be x from its spring equilibrium position, and it's released. What's the maximum kinetic energy achieved by the mass spring system? So we don't have a direct equation for this, but we do have the potential energy of the spring equation, and it reads 1/2 kx squared. And we know from our work energy relationship studies that the potential energy in this spring, once released, could become the kinetic energy of an object. So let's solve for it that way. The amount of the magnitude for the spring constant is 30. And the distance from equilibrium is 0.2. Of course, we'll need to square that. So I'm getting a surprisingly small 0.6 joules of energy that could be released. So my answer there is 4. Okay, and in 25, it looks like we have an object being dropped from a bridge. The object is 1 kilogram in mass, and the bridge is 100 meters above the ground. So we want to know the amount of kinetic energy that after it has fallen for 50 meters. So keep in mind that after it has fallen for 50 meters, we can calculate how much potential energy it has lost, and that would be equal to the amount of kinetic energy that it has gained. So to solve for the potential energy lost, let's just use the equation PE equals mg change in h. And it's going to be 1 kilogram by 9.81 meters per second squared times 15 meters as a change in height. That gives us 490.5 joules of potential energy lost, which of course is equal to the amount of kinetic energy that it has gained. So 490 joules, there's my final answer. 26, we have a spring in a toy car, and it's compressed at distance x. When released, the spring returns to its original length, transferring all of its energy to the car. Consequently, the car, having mass m, moves with speed v. Let's derive the spring's constant, k, of the car's spring in terms of m, x, and v. So we're going to assume there's an ideal mechanical system with no loss of energy, and we need to make sure that the only variables that we use are m, x, and v. So as you know, kinetic energy is 1/2 mv squared. And additionally, the potential energy in a spring is 1/2 kx squared. Thirdly, the kinetic energy that's going to be gained by the object is going to be equal to the potential energy that is stored in the spring. So we're going to use that to inform the rest of the equations. Since ultimately the question wants me to state everything in terms of m, x, and v, I'm leaning towards this equation to start with, and I will use it to plug in to here. So in this step, I've just merely shown that since the kinetic energy of the object and the potential energy of the spring are equal, then by the transitive property, 1/2 mv squared is equal to 1/2 kx squared. Additionally, this gives me the added benefit of introducing m, x, and v into the same equation. So here's my m, here's my x, and here's my v. I'm just going to rearrange now and simplify in some cases, but I'm going to rearrange now to solve for k. So, initially that just basically means dividing both sides by 1/2 x squared to isolate k. On the right-hand side, that cancels the 1/2 and the x squared, leaving k alone. So rewriting, you get 1/2 mv squared over 1/2 x squared, and the 1/2s can drop out. So from there, I think we've arrived at our final answer. We're going to get mv squared over x squared, and I think this meets our requirements because we have to only use m's, x's, and v's, and here we have m's, x's, and v's. So I think that's our answer. So which graph best represents the relationship between the power required to raise an elevator and the speed at which the elevator rises? I remember there was an equation, power is force times average speed, so assuming that the elevator's weight isn't changing, then we're just going to notice a direct relationship between power and speed. Which also seems to indicate that choice 1 is our best answer, being that it's a great graph to show direct relationships. All right, 28 and 29 are related. We have a 75 kilogram athlete, and they're jogging at 1.8 kilometers along a straight road in this number of seconds. It looks like 1,200 seconds. So to determine the average speed of the athlete, we can probably do this relatively simply, using the equation average speed is distance over time. Generally, speed is reported in the unit meters per second, so I converted 1.8 kilometers into 1,800 meters, just multiplying it by 1,000. And we already have seconds. It's in scientific notation, but it's seconds. This is 1,200 seconds. So you get 1.5 meters per second. But when we're asked to calculate the average kinetic energy of the athlete, we can use this speed combined with their mass in the pretty basic equation, Ke equals 1/2 mv squared. So plugging in from there, I just need to make sure that I square my 1.5, but it's pretty easy to find that the answer is 84.375. But with significant figures, we really would not want to keep more than 2 of these digits, so 84 joules is my final answer. So for an object that's thrown vertically upward, it is going to lose kinetic energy as it gains kinetic energy. And also, those two things are extremely interrelated. So the literal amount of potential energy it gains is literally equal to the amount of kinetic energy the object has lost at every moment, as long as it's an ideal mechanical system. So what you would expect is, at least as a function of displacement, the potential energy would be increasing with a direct relationship to displacement. And of course, the potential energy's increase should be matched by a reflection at least on the y-axis. It should be matched by a reflection in terms of kinetic energy. So perhaps it's a bit tempting, but to me, choice 1 looks like the best answer. Okay, so we have a 40 Newton block, 8 meters above the horizontal, so we can calculate its potential energy. And I got 320 joules this time, and one of the things I'd like to point out is that instead of multiplying a mass times gravity to get a weight, I was able to recognize that this already is a weight, so I just did 40 times the height, which is 8. So I got 320 joules of potential energy. But in the sort of subtext of the question, they added that this is not an ideal mechanical system, and this box will lose 50 joules of heat as it slides down the ramp. So that means instead of reaching the bottom of the ramp with a kinetic energy of 320, it's going to reach the bottom of the ramp with a kinetic energy of 320 minus 50, for a total value of 270 joules. Alright, so for 32 and 33, they're related. We have a 65 kilogram pole vaulter, and she wants to vault to a height of 5.5 meters. So we need to do two things. Firstly, in order to do number 32, we need to understand that the amount of kinetic energy that she needs to have right before she vaults is going to be equal to the potential energy that she has at the top of the arc of her flight. So I'm going to solve for her potential energy at the top of the arc of her flight, and I'll sort of circle that back, and then that will become her kinetic energy. So PE is mgh. Her mass is 65, the gravitational acceleration is 9.81, and the height she wants to reach is 5.5, which is this very large number of joules. Now with significant figures, I really should only be keeping 2 of these digits, so my best answer is going to become 3,500 joules with no decimal point. Now in the next part of this 2-part question, we're asked to find the speed that she must have right before she vaults. So we know her kinetic energy, so this is going to be easy if we use the standard kinetic energy equation. We'll rearrange it to isolate V, which on a practical level means dividing both sides by 1/2 m. On the right, the 1/2 m will cancel. On the left, it won't. So rewriting, we have V squared is Ke over 1/2 m. So let's take the square root of both sides to finish this off. So V is the square root of Ke over 1/2 m. Let's plug in. And my answer was 10.37 meters per second. With significant figures, I should really not be going over 2 significant figures again. So with sig figs, probably the best answer is 10 decimal meters per second. All right, so I hope that's been a really thorough review for your Unit 3 exam. And we will do a couple more days of this in class, I'm sure. But use these notes to the best of your ability and study hard, guys. I want you to get 100 on this test. And I believe in you. You can do this. Thanks for watching. Bye-bye.